Alright, this is Mark Anderson for Keller Community College, and we're going to take a look at the introduction to exponential functions, which is going to build in our exponential functions and logarithmic functions unit. And this video is going to focus on exponential movement. And we're going to look at growth and decay patterns. The first two actually in this list here, these are exponential growth patterns. So the reason why they are growth patterns is because the base, this number that is being raised to the power, is bigger than 1. Anytime we have a number bigger than 1, it's going to basically grow by that in like multiplication, but it's actually more of a logarithmic pattern. So for example, if we plug 1 into x, we'd find f of 1 is equal to 2, which I could then fill out in my chart here. And my f of 2 is equal to 4, which I would fill out in my chart here. Now, just with those two, you may not be able to see the pattern, but if I added a third column for some of these, for some of these functions, to the third power would make this 8. So the pattern in this is it's doubling. 2, 4, 8, 16, 32, 64, and so forth. Now, if I plug f to the negative 1 power, or 2 to the negative 1 power, which would look like this, it could be rewritten as 1/2. So there's my 1/2, and if I plug this into the calculator, it would be 1/4, or 0.25. Now, f to the 0 power, or 2 to the 0 power, is going to be 1. In fact, one of the rules about exponents is anything raised to the 0 power is 1, and we had that back in an earlier unit. If we have this equation where we have x plus 1, what would happen is that we would see a shift in this graph, and it would shift left and right when we have the shifting up here in the exponent. Because if I plug 1 into this for f of 1, it then becomes 2 to the second power, which is 4. And then if I plug 2 in for this, for f of 2, then it would be 2 to the third power, which is 8. And f to the negative 1, and if I plug negative 1 into this, so negative 1 plus 1 is 2 to the 0, which then would give me 1. So what this is going to be is that this graph is going to be shifted 1 to the left. Shifted 1 to the left. And this left-right shift, just like you'll experience in finding zeros on the x-axis, or shifting sine and cosine waves in trigonometry, the shift left and right is opposite of what you think, whereas a vertical shift where it's is going to be exactly how you think it should go. But these left-right shifts are opposite of what you would think. So now I have 1, and I know I wrote a 0 there. I apologize about that. It should be a 2, 4, 8. Now we're going to look at the decay. Now, decay graphs are when this number in the parenthesis, or the number that's being raised to that power, is between 0 and 1. Because this is going to take half of the item every single time. Because if I plug 1/2 into the first power, that's just going to be 1/2. And 1/2 to the second power is going to be 1/4. Because it would be 1 times 1 and 2 times 2. Where in this case, I have 1/2 raised to the negative 1 power, which then I could rewrite as 2 over 1, or just 2. So this is going to give me a problem that looks like this, and the other parts are 1/2 and 1/4, and this is going to be 1, and this is going to be 4. So this exponential decay problem starts off with a number, and then it cuts it in half every single time. So it would go 1/8, 1/16, 1/32. And you can see by this, it looks like it's going to shift the pattern. Now we're going to start off by plugging in f of 1. So 1 minus 1 is 0, or 1/2 to the 0 power is 1. So the answer here is going to be 1/2 to the 0 power, 1. And then, well, we're going to plug in the 1 in for this equation, or the 2 in for this equation here. So 2 minus 1. And 2 minus 1 is 1, so 1/2 to the 1 power is 1. So you can see that this graph got shifted to the right, as you'll note that all of these numbers here, if I just plug in these numbers, like f to the negative 1, that would be negative 1 minus 1, so that would be negative 2. That would flip this on its head to 4 over 1, or 2 over 1 quantity squared. So you can see that the decay problems are when your b term, which is being raised to the x power, this b is between 0 and 1, and here the b for the growth functions, where the b is going to be greater than 1. Which makes you think, like, what happens if b is exactly 1? Well, there would be no growth at all, because it would be the same every single time. If I raised 1 to the x power, this is just an example there, 1 to the x power is 1, now 1 to the 4th power is 1, 1 to the 8th power is 1, so as x increases, 1 stays exactly the same. So now what we're going to do is use our technology to graph each equation. Now what's kind of nice about this is I'm going to get each of these up on the screen, and I'm going to graph it, and then we're going to talk about domain and range after we're done. So we're going to start off with y2 raised to the x power, and there's going to be the graph and how it looks. Now you're not going to see a lot just because it's so close to the line that it isn't actually touching it, but we can't actually see a distinction between the two. So we could use the table up above if we wanted to, or we could use this table. I think I want to kind of keep it onto this screen because we're going to be replicating this graph on this piece of paper, which is what the homework is going to want you to do. So let's put the dots on the paper. So our first dot at -2 is going to be 0.25, so it looks like pretty much a softball sitting on the ground. -1 is going to be at 0.5, 0 is going to be at 1, and 1 is going to be at 2, and 2 is going to be at 4. And again, 3 is at 8, and so on and so forth. But this line is never going to touch the x-axis. But this is going to get increasingly bigger and bigger and bigger as it goes to infinity. So this means my domain is going to be all real numbers, because this goes infinitely to negative infinity on x, and infinitely to positive infinity on x as well. So infinity or all real numbers for domain. The real, though, for range, the y is never, ever going to be 0 or lower. So y is going to be greater than 0. Now, the reason why is because if you look at this table, you'll notice it's getting cut in half every single time. So 2 divided by 2 is 1, divided by 2 is 1/2, 1/4, 1/8, 1/16. So as those numbers get closer and closer to negative infinity, they get closer, but they will never touch. They will never touch. Now, if you scroll the table far enough, it will eventually touch because the calculator cannot get more specific past the 10th decimal. But, you know, a half, a third, a half, a fourth, an eighth, a 16th, a 32nd, there's always going to be a denominator. And when there's a denominator, the answer is not going to be 0. So that is going to be why the range has to be greater than or equal to 0. Now let's clear this off and do the next function. The next function is when I take this exact same thing and I move it over by 1. Now, I strongly recommend that if you have the newer calculators where the x showed up in the corner instead of this caret, you may want to click on mode, and one of the options under mode is to, like, your default setting is math type. But what you may want to do is move that over to classic. Now, I don't have a screenshot of that because this is an older calculator, but I strongly recommend that you go back to this classic mode because this makes it a little bit easier to see that the x plus 1 right here is now in the corner. So if I hit graph, you can see that the entire graph pretty much looks the same as the other one, except it did get shifted. So what we are going to notice is that it did get shifted a little bit more to the left here. So let's go take a look as we take a look at the table. There we go. So let's graph this now. Alright, so -2 is 0.5, -1 is 1, 0 is 2, 1 is 4, and 2 is 8. Alright, so here's my graph again, never touching the x-axis, and going to infinity much faster, well, you know, one step, but it is going much faster up if it just gets that one step head start. My domain is going to be real again, and my range is going to be the same as before, where y is greater than 0. But we'll see with this, don't put an equals to sign under here because that means it's touching the 0, which it is not. So for our third graph and our first decay problem, we're going to have our 1/2 raised to the x power. And that is going to give us this graph. It's going to start out high and go low. Now let's go second graph and take a look. Starts out with -2 and 4. So my -2 is going to be over here. -2 to 4. My -1 is going to be at 2. 0 is going to be at 1. And then my 1 is going to be at 0.5. 2 is going to be at 0.25. Alright, so there we go. There's a graph. So my domain's real, because even though it's flipped around, it's still going to have the same properties, and the range is going to be that y is greater than 0. Now what you might ask is, like, is it always going to be this way? For the 4 graphs that we have, yes, it will be, because we're only shifting the graph left and right. I will show you an example, a bonus problem that's not necessarily on this worksheet here, but let's take a look at the last graph, the last picture, before we end here. So on the 4th picture, we're going to type in that 1/2 x, but this time I want the x to be -1 on our table up here. So here we have our x -1, and you'll note that I had to put the x -1 in parentheses because I want that x -1 to be recognized as the exponent in the corner of the calculator. So if I hit graph, you'll note that it's the same swoop, except it was moved 1 to the right, even though it was x -1. The left and right shift, these shifts are going to be opposite of what you think. And again, as I said, just like in when you found when parabolas hit the ground or hit the x-axis, or in left and right shifts of sine and cosine, you can see that right there, that it's going to be opposite of what you think. So here we are, starting off way up high, since this graph got shifted 1 to the right with a -1 on the x. -2 is going to be at 8. -1 is going to be at 4. 0 is going to be at 2. 1 is going to be at 1, and then 2 is going to be at 0.5. So this graph got shifted to the right. Oh, shoot. Yeah, a little swoop. A little tough to do on freehand here. So, domain, real, y, such that y is greater than 0. So there's my set notation. Now, all 4 of these had the same thing. So the big question is, well, Mr. Anderson, I can honestly see that the domain and range is pretty easy from this picture, but what would I need to do to change it a little bit? And one of the bonus problems is, like, what would have happened? Just, hypothesize with me for a second here. What would have happened if you left off the parentheses? So this is x -1. Okay, x -1. Now take a look at the graph. Whoa, what happened there? Well, what happened is that in this equation, we are raising 1/2 to the x power and then subtracting 1 from that value. So that actually moved the line physically down 1. So our domain actually, or excuse me, our range actually goes below 0. So this would be the same thing if I put, like, it's a little bit more noticeable if I put x -5, because now the graph is 5 units down lower than what it was before. It does look like it's hitting a line here at y equals -5, but in fact that's an asymptote line. This is a line that it will never touch. And so I want to go back to this expression and also put it on our paper here and show you what's the difference between this, the way it was written, and the one before it. So I want to show that to you, and I want to show that to you that as a reminder that what we graphed on this grid just a few minutes ago was the expression y equals 1/2 raised to the x -1. Now here's what we have right here. This is y equals 1/2 raised to the x -1. And the -1 is not in that parenthesis. This is the vertical shift up and down in this problem here. So this is shifting the problem down 1. So if I go to my table, you'll note that it's just basically 1 lower than before here. So it's this table, and all the units, everything that I wrote down is now just 1 lower. So that's putting everything below the x-axis. So let's go back to the table and investigate, just so we don't make a calculation mistake, more for me than you. So I am going to put my negative 2 at 3 instead of 4. So my negative 2 was at 1, 2, 3. My negative 1 is going to be at 1. My 0 is going to be 0. And then we're going to start going down 1/2, 1/4. So this new asymptote line, or line I will not cross, is going to be at negative 1. Excuse me. Ugh. I had to sneeze there. So my domain is still going to be real, but my range in this case is going to be where y is going to be greater than negative 1, because the equation of y equals 1/2 x minus 1 dropped the equation down 1 unit from the equation of y equals 1/2 x. So it got 1 lower. If I put a plus 2 here, it would have moved 2 up from this equation right there. Well, I did hope this helped you with graphing. Again, thank you for watching, and stay tuned. This next section I will cover will be in many small parts, because it's quite a doozy to basically do all of section 2 at once. So thanks for watching.